Great, thanks.
Yep.
I don't get their span. Yeah.
Also like city.
Yeah.
Oh, They're a little bit before your flight. Yeah, like. Nah. Hey, you're like, meetings or something. Oh, it's not working. Oh, that's not as bad as it's. I don't know. It's not too bad. Probably why it kept. I'm it's not. Yeah.
You're part of the team. You're part of the team. Including teams. Yes, really? Really? How come you can do that? How come you can do that? How did you play? First. Yeah, but sign up.
Should I?
Romain, why don't you take it away?
Yeah. Okay. All right. So, hi again, everyone. Hello. Yep. All right. I'm gonna get started. I have a couple of things I wanted to say first that I forgot to mention yesterday. So there are some problems that I posted on the webpage. The first one you should be able to do right now. Actually, I think it's something that Sagar did in some way, but it might be good practice for you to do it anyway. The other two problems are more problems for after the lectures to kind of follow up things that I may touch on or not. Unfortunately, I'm not going to stay around too long this week, but if you have any, I'll post solutions, and if you have any questions, you should feel free to email me, and I'm happy to discuss those problems if you have questions and so on. One thing about the notes, the latest version were uploaded yesterday. So if you printed or, I don't know, downloaded the notes like last week, there were some significant updates. Okay. All right. So just a brief summary of what we talked about yesterday. I tried to give you some kind of very general introduction to measurement-induced phase transitions. I talked about how you could think of them as entanglement transitions. I briefly mentioned that you could also think of them as purification transitions or learnability transition. There was something about the information in the measurement outcomes. It's not necessarily obvious that all those concepts coincide, that the purification will coincide with the entanglement transition, for example. But that's something that the StatMake framework that we're going to develop will answer, for example. Okay. So I spent quite some time explaining that it was very important to think of quantum trajectories to actually use the measurement outcomes, and that the transition is invisible in the channel if you average over the measurement outcomes too quickly. Okay, and so the basic intuition that I can give you again is a measurement, if you throw away the outcome, is basically just noise. It's a dephasing channel. Okay. And if you have noise plus the unitaries, you will just drive your system to a featureless state. Okay, so it's really crucial to actually keep the measurement outcomes and do something with them. Okay, whether that's post-selecting or anything. Okay, yeah.
Throw away is kind of a picturesque term. I mean, so if I just write it down, right? I think really what you mean is you're not using it to do any operation.
Correct. You're not using it in any way. In some way, even having knowledge and post-selecting, again, is some action of using the measurements. I mean, if you don't have access to the measurement outcomes, say it's some environment, then that's clear. Then that's a bad.
You don't
do anything with them. Yeah.
Just the,
Exactly. That's what I mean by throwaway. If you ignore them or you don't use them in any sort of way, then you have no chance of seeing that physics. Okay. Yeah.
then you have no chance.
Yeah. Yes. So that's the claim. Okay. All right, so I talked about this post-selection problem, but for now, actually, for the rest of my lectures, I'm going to ignore this. So you'll have to, if you worried about this, you'll have to wait for like Ehud's lectures, because I know he's going to talk about this a lot. And yeah, so today I'm going to start talking about StatMake things, and in particular, I'm going to also talk about the related problems called about random tensor networks, and I'll argue that it's quite similar. So let me start by this problem that I gave yesterday, okay, that I think Sagar talked about. This is kind of independent of the StatMech picture, it's kind of a general fact about the Rényi entropies. So I claim that you can compute this, so rho A is partial, and you want to compute the trace of the nth power of rho A. You can write this as a trace of your system in some replicated space where you copy your system n times, and you have some permutation operator S. And I kind of drew what this looked like in pictures. Just because it's quite important, I'm actually going to write this quite explicitly. So the pictures are nice. And if you're used to the pictures, it's a lot nicer. But what S is, more precisely, is, so it's something that's not going to do anything outside of A. Because outside of A, you're happy doing the trace. Okay, so you want to do the partial trace outs. But inside of A, you should kind of wire your copies together in that way. Okay. And so we're going to do this with some local operator. So I'm going to call this S G X at. And okay, so S acting on X. And it's going to act with that permutation that I call G swap. So the term swap is a bit misleading. Many people use it. So if you have only two copies, what this permutation does is it swap your two copies. If you have n copies, what this permutation does, it's a cyclic permutation. So if you're not used to this notation, so this is labeling a permutation, so it's called a cycle notation. So this is labeling a permutation that takes 1 to 2, 2 to 1, 2 to 3, 3 to 4, and so on and so forth, until the last one, n goes back to 1. Okay, so that's what this notation means, and that's a permutation, so it lives in this permutation group of n elements. Okay, and so this labels how you're going to glue the bra of one copy to the ket of the other copy. So for example, we want to glue the 1 star with 2, 2 star with 3, and so on. And that's what will perform this product here. So what this is, yeah, that's doing the multiplication. And the last one is kind of doing the trace. Yeah. So what this is here, what this S G swap is, it's a representation of, so formally it's a representation of that permutation on that replicated Hilbert space. Okay. So more explicitly, so it acts on site X. Okay, so it's only gonna act in region A. And so it acts on X. And so just to be fully explicit, what it's gonna do is swap labels. Okay, so if you write the Hilbert space on site, so that's on site X. Okay, so I'm going to label my Hilbert space in this way, where you have I1, I2, In, where I runs from 1 to D, so that could be qubits, just 2. Okay, so it's going to take all those states and it's going to map them to permutation. Okay, you're going to take our permutation and permute 1, take our permutation and permute 2. Yeah, so for example, this will be I2, this will be I3, this will be I1. All right, so that's just being fully explicit and formal and writing it as an operator. The picture is a lot nicer. Okay, so if you're used to tensor network notations, people never write those formulas and we're just happy with the pictures. Okay, but formally, this is what this operator is. And it just like implements that permutation. So this, you can convince yourself, implements this matrix product. Okay. And so, so again, I think Sagard did this very explicitly for the purity, where you have only 2 labels. Okay, so this is just the generalization of this, where you have n labels. Okay, so that's a very general and powerful way to think about entanglement and Rényi entropies. And for example, the way people in CFT, for example, think about entanglement entropy is this usually. So it's not specific to circuits or things like this. Yeah.
Like that, well, so that just replaces instead of INs,
Yeah.
By set of IG, right?
Yeah.
So if I think of rho as already that with some coefficient, isn't it just
Oh, so this is going to force the indices of like,
yeah,
the copies to match the other copy, and so that will do the matrix multiplication. Does that make sense? If you write it down explicitly, this will force this index on the bra to coincide with the second index on the ket, for example. Okay, so and that will do the matrix multiplication. Okay, so that's the reasoning here. Okay.
I guess what I'm saying is, like, if you didn't have the S, you could have just written rho tensor product n as rho with the, well, with having the coefficient followed by this outer product. Isn't that the same thing? Like,
I just want to make sure I understand your question. So it's important to rewire things correctly, right? So basically this S hat, if it acts as identity as it does outside of A, the trace is just going to match each tensor product with itself, right? So that's just going to do this. It's going to, right?
that's already not, that's not in.
Yeah, so that's not in S. Or if you want, S acts as identity elsewhere. So there's a so outside of A, it just acts as an identity permutation. And that's what I call here identity permutations. You could imagine, if you want, like, this is being pedantic because this does nothing, but okay, so this does nothing. This is identity. This does strictly nothing outside of A. So
I just mean,
yeah.
Also it's the outer, if you write the computation also has outer product, but it has I1, I2, IN with the ket,
yeah,
I1, I2, IN primes, right?
Right.
Okay, and then I guess this guy collapses.
That's right.
Collapses the primes onto the permutation of non-primes.
It writes of the other copy, right? Yeah. So this will be I2, this will be I3, and so on. Okay. All right. Okay, so keep this in mind. This is something that we're going to use later today. So there was one more thing I wanted to say that's a bit, so keep this in mind, that's something unrelated. Something I forgot to mention yesterday, that I think is quite important. So based on many questions I had after the lecture yesterday, so I think I might have given a wrong impression that one of the difficulties to observe this transition is because entanglement is hard to measure. That is really not the problem. The problem is this post-selection. So in fact, you can actually come up with a version with some order parameter, if you want, that acts on a single qubit, a single spin that will detect this transition. So I will just very briefly explain how that works. So it's an ID due to Garlands in use. Okay, so their idea was like, so you have your initial state, and we're going to take one qubit and entangle it with an ancilla or a reference qubit. Okay. And so this notation here means you form a Bell pair between the two. So it's like up, up, plus down, down between those two spins. Okay. So you take one of your physical qubit and you couple it to that reference qubit. And this is not part of the system. It doesn't, nothing that's on it. Okay. Then you have a scrambling stage. I'll explain why this is useful, but this will delocalize if you want information about that qubit. And then you have your monitored circuits. Okay. With all those measurements and so on. Okay. And the claim is the entanglement entropy of that ancilla. So there's no time evolution on the ancilla. Again, in some steady state going to time of, say, some multiple of L. This is a quantity that just jumps at the transition. So a couple of things I want to mention here. So one important thing is this is still entanglement entropy, but that's entanglement entropy of a single qubit. That is easy to measure. We can do full tomography of a single qubit. That's no problem, right? But this is still in a trajectory. Okay, so that's still nonlinear in the density matrix and so on. So that will still suffer from the post-selection problem. So the interpretation of this is that, so if you didn't have the scrambling stage, and say you were measuring that qubit right away, you will immediately just decouple that ancilla from the system, right? You'll reveal the information about that ancilla, and that entanglement would be 0. Okay. So in principle, a single measurement on that qubit here would already make that entropy jump to 0. Okay. However, so what this scrambling stage is doing, so that's a circuit without, measurements. Okay, so say some circuit with some big hard unitary, if you want. Okay, so this is basically hiding the information of that ancilla kind of non-locally. Okay, so the interpretation of that phase is here the measurements are not able to collapse that ancilla. Okay, whereas in that phase they are. Okay, so again, this has some quantum information, interpretation that I won't go too much into, not to overlap too much with the other lectures. But what I want to emphasize here is that, this is a single qubit observable. Okay, so you don't need to measure entanglement. Yeah, measuring entanglement is not the issue. Post-selection is. Yeah. Yes.
So I think this job is for
Correct. Yeah.
so for
Correct. Yeah. So if you do this for a finite system, if you do this in actual numerics, this is going to look like a nice. So this has a crossing, and this will sharpen as you increase system size. Okay. And you see, they see this very nicely in numerics. Yeah.
The last time you talked about 3 things, like the learning, the entanglement,
And the purification.
purification.
Yeah.
And you didn't. This scrambling is the thing that gives you identity, initial state of the identity.
Yeah. So the scrambling is important to avoid having that issue of measuring that qubit right away. So if you didn't have the scrambling stage, you wouldn't have like just a step here, because measurements would be able occasionally to just collapse the qubit.
The last time you described you feed in the infinite temperature.
Right.
Is that what I should think of?
Yeah, so this is closely related. Like, if you want to feed in, like feeding an infinite, mixed state is like imagining that you couple each qubit to an ancilla. Okay. So again, so this is something I know Sarang is going to talk about. So like if you have a setup like this, so you have like n reference qubits, if you trace over those ancillas, that's effectively preparing of infinite temperature mixed states. Okay, so you can think of the purification transition as kind of entanglement between those qubits and those reference qubits. Okay, but yeah, a single ancilla will have this nice jump. Okay, so that's why like this, when I was talking about purification, I had like this S over L, and it was like going to 0. You can think of it as kind of the density of ancillas surviving the measurements in that picture. Okay, does that make sense? So this is saying that like your infinite temperature mixed state, I can purify it by considering that initial states where each qubit is coupled to some ancilla. That makes sense? Yeah. So this is the same with the single ancilla. Yeah. How deep is the circuit is the question? Yeah, so the scrambling circuits, let's say it's like, order L. So I want to make sure that things are completely delocalized. You could think equivalently, you can think that's a one big Har unitary. Okay. And this one, I'm imagining, like in the purification, say polynomial of L, but practically, let's say just a multiple of L, like 4L or something. Yeah.
What happens if you, instead of measuring the qubits, swap them, and then later trace out the qubits you swapped away?
So sorry, can you repeat the question? So
what happens instead of measuring that qubit,
Mhm.
swap it with a fresh qubit in the 0 state,
Mhm.
and then all the swapped qubits, you trace them out later on as well?
So the question is, okay, so what happens if I don't? So I don't really measure the qubit here, right? Oh, so in the monitor circuit, I don't touch the ancilla, right?
Exactly. And
Yeah.
instead of measuring the qubits in that part of the circuit,
Mhm.
swapping them with the 0 qubit,
Mhm.
and then later trace out all the circuits to.
Okay, so I think Ehud actually is going to maybe talk about this. So let me postpone that question because I think he had a version of that. So yeah. Yes. Okay. Oh, I mean, I'm just saying, you know, so I mentioned yesterday that you could think of this purification as like encoding qubits and information. And so, and yeah, and I know Ehud and Saring are going to talk a lot about this. So, okay, so, all right, so let me now actually focus on like, so starting now, I'm going to be a bit more precise and explicit. And so I'm going to talk about stat-make approaches, but first I want to mention a third example of transition, which apparently is unrelated to measurements, but it shows very similar physics, and it will also be nicer from the stat-make perspective. And so that type of entanglement transition that you see in those measurements, you know, in those monitored circuits also shows up in a somewhat different context of thinking of random tensor networks. Okay. So what do I mean by this? So you had lectures last week from Frank Polman. You know, we mostly talked about matrix product states, where you have like, you know, so a matrix product state will be something like this. You have like bonds with bond dimension capital D, and you have physical degrees of freedom, let's say qubits. And again, I'll denote the dimension small d. Okay. So let me imagine kind of a more complicated tensor network that doesn't have like this 1D structure. So I'll define things properly. Let me imagine you kind of have a square lattice. That kind of keeps going. Okay. And so on each node here, you have a four-legged tensor. Okay. Where like each link means you contract legs and force them to agree. And so each index runs from 1 to capital D, where capital D is the bond dimension. And so this object is still, you should think of it as a wave function, kind of a 1D wave function for the system living on top. Okay. So you still have like on each side. Sorry. Okay, so your Hilbert space is still this. You have L, Q, dates or qubits. Okay. But that wave function is given from like contracting that big tensor. Okay. Does that make sense? So on each node you have a tensor, and again the link, like just like you saw for circuits or for like MPSs, means you force those two, you know, you sum over the two labels and force them to agree. Okay. So the claim that I'm going to make is that this is actually not, you know, this looks very different. There are no measurements, there are no unitaries, no time evolution. But I'm actually going to claim this is very similar. Okay. And the way you can think about this is, okay, so I can label this as space, and I can label this as time, maybe imaginary time if you'd like. Okay. Or you can imagine maybe you had some kind of initial state. So your initial state was an MPS. Okay. That's like the bottom layer. And then you kind of like time evolve by acting on your system with like those layers. Okay, so in the matrix product state operator language, this layer is a matrix product operator. So it's an operator because it has like brides and cats. You have like incoming legs, outgoing legs. So you can think of it as, yeah, a matrix product operator or an MPO, but you can basically think of it as some type of time evolution. Okay, but it's non-unitary. Of course, I don't have unitaries here. Okay. So this big tensor network, you can think of it as formally as some type of non-unitary time evolution that produced in the end that wave function that you have. Okay. Right. So for now, I haven't really defined them, but like, so what I was, going to mention is just like you can consider random circuits. It's a natural question, and that's something, many people, including myself, thought about. Is you could say, okay, what are the properties of such wave functions if you take those tensors to be random? Okay, so you can take those guys to be just random Gaussian variables. No. No. So you just take them to be Gaussian. They don't need to be, they can be complex numbers, no problem. So uncorrelated on different sites and different labels. Okay. So this is still a well-defined problem. Okay. And the claim that I'm going to make is that this is not exactly the same as the measurement-induced phase transition. And what's missing there will be the Born probabilities of the measurements. But this setup can also have like those entanglement transitions. Okay, so basically that wave function at the end, if it were just an MPS, one layer, it has area law entanglement. But since you had all that evolution, it could be more entangled or less. Okay. Right. So it's a good question. What are we actually tuning? So you can tune various things. So you could put some constraints on the tensors, like Leo was saying, and maybe tune that. One thing that you can tune is the bond dimension. Okay, so there's a caveat of how you tune this continuously, but I'll get to this. Okay, so we're going to tune the bond dimension of the tensor. So each link here, again, has bond dimension capital D. Okay. And the claim is, as the function of capital D, you also have an entanglement transition. Okay. So there's a critical D. So if D is small, so in particular, if D is 1, then you just have a product state. Nothing happens. Claim is that your wave function psi can have area scaling of entanglement, in that, but there's an actual phase. And above DC. Okay. So the caveat here is D is an integer parameter in the way it's defined. Okay, so let's say DC could be, I don't know, 2.7 or something, but it would mean that maybe for bond dimension 2, you would be on the area law side. And bond dimension 3, you would be on the volume law side. Okay. So here, the entanglement of that wave function goes as a constant. Here, the entanglement will scale as LA. So again, here the perspective is very different. You don't have the measurements, you don't have circuits, but the intuition that you should have is if you take a random quantum circuit and you start putting the measurements, you break unitarity anyway. Okay, and so the intuition I would like you to have is it's not so different from a tensor at the end of the day, right? So unitary is some four-legged tensor, right? But it has some structure, and the structure is unitarity. Okay, so tensors don't have any constraints like that. But the point is, once you start adding the measurements, you break unitarity anyway. So maybe that's the intuition that I can give, that you can have transitions as well here. Okay, so this is very similar to the measurement-induced phase transitions. Even though it's actually not exactly the same, it will not have the same critical exponents. And for example, yes.
Sorry, you mentioned it's non-unitary, okay, but where does this distinction come between like deep coherence and the
Yeah, so here I don't. Good. So here I don't really have that picture, right? But here I also don't have a, the post-selection problem came from like trying to implement that circuit in practice, right, in an actual experiment. Here I don't, it's a non-unitary evolution anyway. So if you wanted to prepare that wave function in this way, you would need to find a way to realize that non-unitary evolution in some way, and you would run into the same problems. Okay, so here I don't really have the analogy of like, okay, but this is not something you would naturally realize in a quantum processor anyway, unless you had a way to realize that non-unitary evolution. Yeah. Yeah. Mm-hmm. You know, I mean, so it's a good question. So the question is like, how universal is this? And like, can you, if you change the properties of the tensors, how sensitive are the physical properties of the transition? So the answer is, yeah, so it's fairly generic as long as you don't constrain your tensors too much, at least we believe it is. So the width of the distribution doesn't matter too much. So I'm actually going to I'm going to refer to the average over the randomness of the bar. Like we'll take the average of the tensors to be 0. And then we'll have like tensors on side I, tensor on side J. Okay, so just to be fully clear on what the Gaussianness means. So what this will do, so like tensors on different sides are uncoordinated, so that there's a delta ij, and then the Gaussian average will just force all the indices to be the same. So just saying that you don't have correlations if you don't have. And the strength here doesn't matter if you take the average to be 0. If not, it would have different properties, but yeah. So the width of the distribution is not going to matter. Okay. Yeah, so here like higher moments are going to be given by Vick's theorem because I take them to be Gaussian. Suppose we take them to be non-Gaussian. So it's a bit tricky because we only know how to calculate things with Gaussian. So then you can do numerics. But yeah, it's believed, I strongly believe it doesn't matter. Yeah. Yeah.
T still poly
No, well, yeah, well, something in, I will actually take it as scaling as L. Let me not do poly. So something is, I want the depth to be at least the number of qubits. If it were less than L, then you couldn't really realize volume law entanglement. You could not. So you need to have at least L layers over there. It will be kind of clearer when we talk about domain walls, but if you don't have a sufficient layer, you can kind of cut through the circuits. Yep.
Well, that's which was periodic in the time direction. Okay, but
yeah. So you could, yeah, so there are variants of this, just like for random circuits. So you could imagine that like the tensors are like inhomogeneous in space, and then you repeat this. You could take like a clean tensor network where all the tensors are the same. So we've actually been thinking about this. And even in those contexts, you can have entanglement transitions. So you can take this to be actually clean. Okay, so the motivation is again a little bit like in random circuits, right? So we take things to be completely random, hoping we get a generic behavior. But if you take, as long as you, of course, you can kind of cherry pick your tensors to find something exotic if you pick just one. But the randomness or the flow-k-ness or whatever doesn't really matter too much. Yes. Very good. So let me address this. So the question is, okay, so D is discrete. So how do I tune D here? Okay. So this is true, but D can be made. So the answer is we can make it continuous. So let me address this before I go back. Okay, so you just write this. So this is so this is very similar to MIPTs, but there's no bound probabilities. So how do you make D continuous? This is a little bit of a tangent. So like if you don't, let me just briefly mention how you can do tensor networks with continuous bond dimension. So the way to do that is as follows. So one way to think of a tensor network is using the so-called PEPs, or projected entangled pairs construction. For those of you who know what the KLT state is in 1D, this is actually very similar. So you can think of a tensor like this. So you have a tensor and it's contracted with its neighbors. So you can think of this as follows. So you can think of the tensor So you can think of the tensor T as a state. So it has a bunch of indices that are going to be summed over. So basically, where I have the tensor, I'm going to imagine that I have like multiple spins. So here 4 of them, where those labels run from 1 to capital D. Okay, and from the components of the tensors, I can construct a state. Okay, so far so good. Okay, so that's a state. So now, how do I do the contraction, right? So now I want to contract that tensor with its neighbors. And so the thing that we're going to do is project onto Bell pair states. Okay, so if you want, it's a measurement in the Bell basis. So you can project onto Bell state, where the Bell state is just a maximally entangled state. So this is a way of like that whole tensor network that I wrote here, you can reinterpret in this language. So I had, every time you had the tensors, you had like those states T, okay? And then you do a projection in the Bell basis. You project those spins onto Bell pairs. And what the Bell states will do is force indices to agree, right? So here, for example, if you had mu, and if you had mu prime here, the Bell projection will force those indices to be the same. And that will give you the contraction, okay? So this is a general construction that's known as PEPS that you may have heard about. So in 2D, if you know the AKL state in 1D, it's kind of a 1D version of this, where you have some state and then you do projection onto Bell pairs. Yeah. No, I mean, there's just this state here, but you just have like this projection onto singlets. That's the analogy. So, okay, so this is just a way of rewriting a tensor network. But the nice thing here is now you can actually, for the same tensors, you can change that state. Okay, so let's say instead of projecting onto a Bell pair, you could project onto something less entangled. Effectively, if you do that, you can tune the bond dimension, or you can realize some fractional bond dimension. So it would not have an interpretation in terms of a tensor network anymore, but it's kind of a generalized tensor network. So you take this is a maximally entangled state. You take something that's less entangled, and that would effectively realize fractional bond dimension for you. Okay. So if that didn't make a lot of sense, that's okay. That's not important for the rest of the lecture, but I just wanted to mention it. Yeah.
Also involve the capital P. In other words, there's a prefactor there.
Yeah.
That controls like
Mm-hmm. Yeah, so like this transition is going to be in the regime where both time and like L go to infinity. Yeah, L is the number of qubits of physical legs. And I also want the depth to go to infinity. If it didn't, then it wouldn't have the volume law, actually. Like it would. Yeah, and the prefactor will, I mean, we'll see, like at large bond dimension, it will go as log D. As it should, that's kind of the maximal. It could be entangled, but in general, it will just have a prefactor that will smoothly evolve. Yeah. Yeah, so the full claim is that wave function at the end of the day is take a tensor product of all those states T on each side. Okay, and you project them onto those Bell pairs on links. Okay, And that gives you a wave function at the end. So that's the formal construction of the wave function. Okay. Yeah. Yes.
State is unnormalized.
The state is not normalized. That is correct.
So the scale is from.
Yeah, I'm going to get to this, and that's actually a crucial feature, and it was also true for measurement-induced phase transition. You had to normalize things because of measurements. This will need to be, in order to, when I define entanglement here, you need to normalize your wave function properly for it to be meaningful. Yes. Mm-hmm. Yeah, so this transition in the tensor network language actually has a nice interpretation of like hardness or complexity transition. So you can think of it as one big 2D tensor network. And the way people would typically contract a 2D tensor network like this is by doing some time evolution precisely like this. So using something like TBD that you saw last week. Okay. And so this transition tells you that, you know, there's a phase in which like that state is actually going to evolve to something volume law. And that tells you that this calculation is going to be hard. Okay. Here, okay, I'm putting quotes because it's not entirely, you know, okay. I think Frank talked about this last week. It's not immediately obvious, and it depends a little bit on the Renyi structure and so on, to go from area law to being able to have a nice MPS representation. But being a little, ignoring that caveat, you know, you have an easy phase where you could do TBD and represent your state with an MPS. So you could compress this whole thing into an MPS, whereas there's a phase where you cannot. Okay. And so that phase transition has some interpretation as a complexity transition in that language. Okay, which is important, and it tells you whether you can do that 2D tensor network calculation or not. Yeah. Yes. Yeah. Yeah. Okay. Yeah. So, okay. So I'm just like claiming in order to realize something that's less and that has effectively fractional D, it's not unique. What you can do is replace that state you project on by something that's less entangled than a Bell pair. So put some coefficients here. Okay, like. Well, that effectively, okay, I'm just, that allows you to interpolate. If you tune the entanglement on that state, that allows you to interpolate between different integer bond dimensions. This is not unique. I'm just saying that's one way to interpret what it means for D to be continuous or fractional. Does that make sense? Yeah. Yes.
Wondering, in the random quantum circuits, this probability of measure, this is like a physical thing.
Yeah.
But here for the tuning the bond, I think they're going something they something I would choose right off the bat. They're like a
Well, so like the physical interpretation of those transitions is widely different, right? So this doesn't have a natural interpretation in terms of an experiment or anything like this. Like I said, the interpretation, the way I like to think about this is, like I said, a complexity transition. You know, if you care about doing numerics on those tensor networks, it tells you there are phases where you can do the calculation and phases where you can't.
So
That's
you can do it. You mean that the like the error you get is low? Is this what you mean, or is just you setting you to forget about whatever happens?
Right. So what I'm saying is like any sort of 2D tensor network calculation is actually going to be done by effectively doing a 1D evolution. That's how people do those calculations. And so it's important. So effectively, it's doing TBD that you learned about last week. So having volume law will be a problem. And it means that that calculation is going to fail. And so that's going to tell you that that tensor network contraction cannot be done. Okay. And capital D happens to be the parameter that you tune in those calculations. So there is natural. Okay. So, but I appreciate it looks unrelated. Okay. But like the only intuition I can give you at this point is that it's non-unitary evolutions. And you'll see that on the StatMech side, they're going to look almost identical, like those problems. Yeah. Can you repeat the question? Right. Okay, so the question is the transition here really the same as the measurement-induced phase transition? And the answer is that it's similar, but it's actually different. And the key difference doesn't really come from, I mean, it comes from the fact that you don't have the Born probabilities. And we'll see this. So like in the measurement problem, we were waiting all, each configuration occurred with that Born probability. Okay. Whereas here, I'm just going to, like, different tensors will just be weighted in the same way. And that will turn out to be the actual only difference. Yes. So I'm going to talk about this right now, but yes. Yes. Mm.
So imagine I would start with a one dimension.
Yeah.
Then say we get
Correct.
now if I decrease the bond dimension, do you not directly basically also lower the maximum entanglement that I can get? Is it from that not somewhat again if we have some really small bond dimensions that cannot get a one?
Well, so it's kind of the extremes are clear. So you're right. I agree with your intuition that if when you take D to infinity, it's clear, probably intuitive, and actually there's something like minimal cut that will apply, and that you will have something like volume law. It's also clear if you take D equals 1, you have a product state. You have, okay. So the only, but that only, the non-trivial maybe part is like you have actual phases that extend, right? I mean, it's also clear in the measurement problem. If you take P is 1, you have product state. If you take P equals 0, entanglement just grows. But yeah, it's fairly natural that maybe you have actual phases. But that's the right intuition. You have those two extreme points. The claim is that behavior persists in two phases. So is the question, what is interesting about this? Yeah. Well, so like I said, like the universal properties of the transition is, so this is related to the measurement problem if you do what's known as forced measurement. That is to say, you just pick one, for example, you post-select on having all your measurement outcomes being 0. Okay, so it's kind of a particular case of the measurement problem, and this happens to be related and the same. Okay, I guess like the reason why I'm talking about this is kind of twofold. So one, I just want to mention that like those entanglement transitions occur whenever you have non-unitary circuits. You don't need measurements. Okay. The other reason is purely kind of technical. The StatMech description of this is a lot easier than those half circuits. So this will just make my life a little easier. Okay. Otherwise, I'm just basically claiming this is almost the same as the measurement-induced phase transition with that caveat of the Born probability. One interpretation of the measurement-induced phase transition is in terms of complexity transitions. Okay, so as I mentioned, the measurement-induced phase transition, you could also ask the same question. Why is that interesting? Since I mentioned this post-selection problem, you could say it's unphysical. You could say it's maybe very hard to observe. You could even question whether that's an actual transition. I think my answer to this, and again, maybe different people will have different answers, is that's not the right perspective to have. You can have different ways of thinking about those transitions. One of them is in terms of this learnability. One of them is in terms of quantum error correction and like information. And one of them is in terms of those complexity transitions of telling you, some phases where some task will be hard and some phases where some task will be easy. Okay, which is a whole field in itself of asking about complexity. And the fact that you can have transitions in that regime is important. Okay, so, depending on how much you care about tensor networks, maybe that doesn't appeal to you, and that's fine. But I just want to say that I feel this is kind of the general theme for those measurement-induced phase transitions, that you have to have a perspective like this for them to make sense. Okay. Yes. Yeah. 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 Yes, thank you. So that's a great question. So the question is, if you take the measurement-induced phase transition and you just happen to weight all the configuration, all the trajectories with weight 1 instead of the Born probabilities, is it the same as those tensor networks? And the answer is yes. That's precisely the case. Okay, so that's actually the only difference really between the two problems. Is if we lived in a world that didn't have Born probabilities, then it would be the same.
interpretation that you gave.
Yeah.
Does that allow me to do this tensor network as a measurement of the process? Because a Bell measurement,
Mhm.
when you're projecting onto the Bell plate.
Mhm. Yeah. 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 That is correct. So yes, you can think of this projection onto Bell pair as a measurement in the Bell basis. That would absolutely correct. So I'm post-selecting to that exactly. Yeah, I'm post-selecting on that outcome of just getting the singlet. Yeah.
So you could have choose your ensemble of operators and then also made measurements to form probability.
Yeah.
And then you would get.
Correct. Yes. Not that I know of. I mean, like, the measurement-induced phase transition is already hard to realize experimentally, as I mentioned. So you already have to work around post-selection. This you could if you could do post-selection in the same way, right? So my answer is if you can go around the post-selection problem, you can do what Vedika just said. In principle, yeah. Sure. Yeah. Yeah. So you have to go around the post-selection problem in the same way. Yeah. So. Yeah. Mm-hmm. No, so the entanglement is the entanglement is bounded by small d, right? So the maximal entanglement that you can have is log d times LA, right? So d is the physical. So since d is 2, you would have qubits. Capital D is the bond dimension. So you have like the physical dimension and the bond dimension. Yep. Yes. Can you repeat that? Mm-hmm. Yeah. Okay. So the question is higher D more akin to something that looks unitary? Not really. I mean, it will have like a minimal cut, like you've seen with Sagar last week, but nothing is unitary here. There's really. Yeah.
Was this transition in these random tensor networks?
Yeah.
Appreciated after the
they sort of precede roughly at the same time, I would say. Like we were thinking about it at the same time. Like so the earlier random tensor network papers were in 2016, so that was before, but they were not discussing transitions, but it's a completely different context, right? And it was also not obvious in any way that they would be related, and that only came after. All right, so lots of questions. It's great. Let me actually try to say something about stat mappings. Is really what. Okay, so let me now like switch gears and say more about those statistical mechanics mappings and what we can say with them. Okay, so I'm going to show that you can have an exact mapping of various quantities. I'm going to focus on entanglement. So I'm going to focus on like those Renyi entropies, maybe changing notations a little bit, onto a classical StatMech model. So why is that useful? Well, we know a lot more about classical statistical physics than we do about entanglement properties or unitary evolution or like measurements and so on. Okay. And in particular, it can give you some really nice qualitative feature or picture of the transition. And in some cases, it can give you actual solutions. Okay. So you saw part of this with Sagar last week, which is great. So you saw that you could map the purity to some Ising model in circuits without measurements. So here the complication is going to come from the fact that we're going to need so-called replicatric or replicas, not only because we have to average a log or something like Sagar discussed last week, but intrinsically because of the problem. And the problem is that things are not normalized naturally. We have measurements you need to normalize because you lose weight. Those wave functions are not naturally normalized, so you need to normalize them. Okay, so this will make the StatMech a bit harder. But let me actually mention the qualitative picture right away, because that's really the most important thing. The key result that we're going to show is that entanglement will be related to the free energy cost of domain walls. Okay. Which should not really come as a shock from what you discussed with Sagar last week. Okay. So there'll be a relation between entanglement and domain walls in some StatMech model in some magnets. Okay. And the difference is, so we're going to tune some parameter like P in the measurement problem or the bond dimension D in this random tensor network problem. And this will roughly be related to temperature in that StatMech model. It'll actually be like more like inverse temperature. Okay, so we'll have two phases. And so that StatMech model will be basically a classical magnet. So, okay. So think of it as almost an Ising model, but it will be more complicated than an Ising model. And that Ising model, let me actually just use D. That Ising model will have two phases. It will have ferromagnetic phases. And it will have a paramagnetic phase. So you'll have either a ferromagnet or paramagnet. So that's StatMech model, if you want, will be ordered as these are. And entanglement will be, so what do I mean by inserting domain walls? So we'll have, getting that picture that you saw with Sagar for an Ising model, we'll have something like an Ising model that says it's a ferromagnet, all spins are pointing up, and we'll have some region at the top I'm going to call A, where I'm going to force the spins to be set down. Okay, and that's what it's going to mean to have like what I'm going to mean by having a domain wall. And the free energy cost of like inserting a domain wall like this is something that will, ferromagnets domain wall has a finite line tension. So this will actually scale with the size of the interval. So delta F will scale as LA. And so that's entanglement, and that will correspond to volume law. Okay. In contrast, if your Ising model, say, is disordered, doing this actually doesn't cost extensive energy. Okay. And that will correspond to area law. And that's because a paramagnet is a domain wall condensate, if you want. So you have domain walls everywhere. So creating one more doesn't really change much. And so that doesn't really scale with the size of the interval. Okay. And so, of course, that also gives you, in principle, a handle on the transition, right? Because unfortunately, it's not just going to be an Ising model, but at least it's just some classical transition, ordering transition. Okay. So that's the qualitative picture that we're going to derive. Let me just say a few more qualitative things.
You've got a qualitative difference, although physics-wise it seems the same. If you introduce A and A complement, the domain is Sagar talked about domain wall running all the way down. Then in the StatMech model, the weight, at least in a unitary guy,
Mhm.
the weight of a triangle with no, sorry, there was the weight of a triangle pierced by a horizontal domain wall was 0.
Yeah.
So then the domain wall could not return
Okay.
of the bottom.
Mhm.
Here,
Okay.
it's the reverse.
So, I mean, like, okay, in a purely unitary limit, it's true. So the question is, you have constraints from unitarities that, you know, force some particular shape on the domain wall. That's true from unitarity. This is not really going to be crucial for me. It's still true if you have like a unitary circuit with measurements. So the domain wall would look something like this in Saga's case, where you, because of the constraints, it has to have like this light cone shape. But in the random tensor network, I won't have that constraint because it came from unitarity. And once you start adding measurements, it's still there, but I would argue it doesn't play a lot of role physically, so I'm going to ignore that. But yes, in principle, you can have constraints on what the domain wall is actually doing. Some particular configurations locally as are 0.
You don't have a 0.
Not in the tensor network problem, for sure. And once you start adding measurements, you still do. I mean, but not in a way that will really affect the physics, so I'm not going to talk too much about that. Okay. So one important consequence of a stat-mech mapping is that the transition is described by a conformal field theory, a CFT, that describes, you know, that transition, that ordering transition in the magnet. And that's something kind of very non-trivial. You know, you can have, it means you have some, in particular, you have some relativistic invariance, some scaling, you know, scaling with time. You have a dynamical exponent 1 that relates space and time, which is not obvious at all, at least a priori, if you just look at the problem. But you actually have full conformal invariance. And this will also tell us that different Renis will scale logarithmically at a critical point, and so on. Okay. So I'll talk about this. Importantly, this is very different from, this is not like a central charge. Let me emphasize this right away. We'll talk about this more, but this will come from some boundary properties here. Okay, so how do we actually do this stat-mech derivation? So I'll do it both for the random tensor networks and the circuits with the measurements. So you'll have 2 versions. So the one with the circuit is more complicated. It will involve this Weingarten functions that you saw with Sagar last week. The tensor network case is actually a lot easier, and I can explain it without, you know, a lot of formalism. So, yeah. So Z is a dynamical exponent. So this relates the scaling of space and time. So this is just saying that here things are isotropic if you want. I mean, there's maybe a constant velocity if you want between the two, but otherwise you have the same scaling in space and time. Yeah. Both. They're all the same. Yeah, so they could be different CFTs if you want, but they will both have this dynamical exponent to be 1. Yeah. Yeah. I will mostly, you know, one of the things I'll try to convince you is that they mostly essentially the same problems with that tiny caveat of the bond probability, which. So if you change the way you weight your trajectories, it's going to change the exponent. That's the claim. If you change the way you weight your trajectories, okay, so you can think of the bond probability as like a Boltzmann weight for your trajectories. And so as Vedika mentioned, if you weight all your trajectories with 1, you'll have this forced measurement problem of the random tensor network. If you weight them physically with the bond probability, you'll have the measurement-induced phase transition. No, they have the same Z. The Z dynamical exponent is always 1, just a property of conformal invariance. Yeah. Okay, so let me first focus on those random tensor networks. So we want to compute something like a Rényi entropy average over the tensors. Okay. So I'm going to denote by a bar averages. So we want to compute something like this, where the bar refers to averaging over the random tensors. In principle, I want the behavior in a typical tensor network, but we'll assume that this is self-averaging, so we can just average and do that. But let's say we want like that quantity average over that ensemble of tensors. So the crucial thing is we need to average a log, but more importantly, I had to normalize my wave function. Okay. So even if I wanted to compute, say, purity, it would not be easy here because you would have a denominator. Okay. So that's so the problem that we're faced with is we need to average a log, or like equivalently, if we wanted to compute something like purity, we need to average something that's in a denominator, okay, which is hard. And so the way we're going to do this is using a replica trick. Saga briefly mentioned last week. So this is just going to be based on this identity, which is just a correct mathematical statement, right? You can just check that formula is always true. And the idea is like, in order to compute the average of log x, we're actually going to compute instead the average of moments of x. But the caveat is we're only going to do this for k integer. And then we'll try to analytically continue k goes to 0. Okay. So let me write this down in this case of like the entropy. So using just that formula, I can rewrite the two logs in there as averaging trace of rho A to the n to the k minus trace of rho n to the k. Okay, so the only thing I did is use that formula over here to rewrite the logs over there. Okay. And the claim is that those quantities are going to be easier to compute, like averaging over the randomness, whether it's unitaries or whether it's like a tensor network, is going to be a lot easier to do those moments here. Okay. So this quantity I'm going to call ZA by definition, and this one I'm going to call Z naught. And we'll see they will correspond to partition functions. Okay. So I can rewrite this in a more suggestive way by introducing free energies. So the usual way, I'm going to define F to be minus log Z, no temperature here. And I can rewrite the same as follows. Just have a sign change. So basically, I replaced the difference between partition functions as the difference between free energies. And the reason is I'm essentially taking a derivative with respect to k, if you want. That's what this 1 over k is doing. And when you take derivative of the log, you'll have derivative of the partition function, and you'll have 1 over the partition function. And so this equality is true because the partition functions are both 1 and that limit k goes to 0. So if that's not obvious to you, you can just do this. It's a simple algebraic exercise to write this. Okay. So I have yet to show that those guys are actual free energies, but you see already that I'm closer to my goal, which was to say that the entanglement entropy was related to a free energy cost of doing something. So I rewrote this. I rewrote entanglement as this difference of free energies with the caveat that I have this replica limit. Yes. The exponent, so the question is the exponent in the denominator inside or outside the trace? Here, you mean? Yeah. Right, that's, yeah, so let's put it outside. Yes, thanks. Yes, thank you. Thank you, good question. Okay, so this is so far just standard algebra. Any question about this? Does the, yeah. Yeah, thanks. So the question is, can I explain a bit more like that step going to FA? Yeah, so one way to rewrite, I can rewrite that replicatric as maybe it's easier thinking of it as a derivative. Okay, so I can write it in this way. That's also true. Okay, and so here you're taking a derivative of a log. Okay, so if you take derivative of the log, that's derivative of. Oh, I have a 1/k. That's like the same as having the derivative because it goes to 0. You can, okay, maybe if that makes the formulas easier, replace the 1/k by derivative. They're both correct, right? You agree this is correct? Yeah, I have a 1/k. I have derivatives on both sides. Okay, so like I'm saying, if you take derivative of log, that's derivative of ZA divided by ZA, but then that limits ZA goes to 1. Okay, so in the limit k goes to 0, this is just ZA prime. So I've just shown that the derivative of the log is the same thing as the derivative of the partition function. Okay, so I'm saying that inside that derivative or inside this 1/k, you can just replace the two. Okay, does that make sense? No. I mean, the other way I can. So let's see if I. Well, okay, so if you don't like the derivative, like you agree both formulas, this one you agree is correct, right? Yeah. This one with the -1 is also correct. We agree as well? Yeah. So I'm just saying, like, if you use the top one, you get that formula with the 1/k. The -1s cancel between the two. Okay, so I'm just, whether you put the 1/k or derivative, it's up to you. I just find it easier to use the derivative to explain this.
Maybe an easier way to do it is instead of writing xk minus 1 in the numerator, you can just write explicitly log x to the k with the average side of the logarithm.
Yeah, that's correct. Yeah, that's also another way to do it. So yeah, basically, like I'm basically like inverting the order of the, the replica limit allows me to average inside the log inside. Okay, that's kind of what it does. Okay, so if you're still not convinced by this, this is simple algebra in the sense of, this is just Taylor expanding this. If you want a small k, and you can check that it works. Yeah. Yeah, so I mean, I haven't shown that this is a partition function yet, but I'm going to show that ZA and Z0 are partition functions, and I'm calling F minus log Z, and so I'm saying those are free energies. Yeah. Yeah. So I'm saying both formulas are correct. So you can either think of it as a difference of partition functions, but that's not the most intuitive. But it's easier to think of it as a difference of free energies. And the reason is an equal sign is the partition function is actually 1. And that's actually a feature of this replica limit. The partition function itself is trivial. Okay, so you're subtracting like those both partition functions. You can see if you take k to 0, they become trivial. Okay, but that limit dividing by k still gives you something non-trivial. Well, I haven't really explained how, like, why the partition functions yet, right? So if you agree those are partition functions, then I can just define free energy. They're just my choice, right? I define this as the free energy. Okay. So the replicatrix can be subtle, right? So there's going to be something sketchy in what we're doing. We're going to take n and k to be integers. So k is going to be a replica index. N is the Renyi index. We're going to take them to be integers, but then we want k to 0. Okay, and that can be, if you think about it, it can be problematic. No, there's no approximation except doing that analytic continuation in the end. So that will be the tricky part. So I'm going to call Q the product of n times k. And so that's the number of replicas, if you want, or it's the number of copies of my density matrix. You can see it here, you have k times n, and here as well. You can think of it in that replicated space where now you have like this trace of rho h with the n, you know, but I took it to the k, so my density matrix enters n times k times. Okay. And the whole point of the replicatrix is that averaging moments or powers of the density matrix is going to be easy, or at least doable when that number is an integer. Okay. But the issue is at the end of the day, we want to take Q to 0. Okay. So why is that easy? Well, you've seen, so if we had unitaries, that's what we'll do tomorrow. You've seen with Sagar how to average moments of unitaries. Okay, so that involves those Weingarten functions. If you're thinking of the tensor problem, which I'm going to focus on here, we have to average powers of tensors. Okay, so so I unfortunately erased like my formula. So if you have, you know, my average of the tensors is as follows. So the way you average over tensors, so on each side, so on different sides, the tensors are uncorrelated. Like on different sites, unitaries are uncorrelated, and that will force indices to be the same. Actually go. Here I'll need some space to actually draw what's going on. So we have two things to do. We want to average over the tensors that are random. And we'll have to do with like what we do with the top boundary. So the top boundary will, you know, tell us what type of trace we're doing. So that will distinguish those two partition functions. Okay, so in one, we'll do this partial trace, and we'll have to glue things in different ways. So let me ignore the boundary for now and focus on the bulk. So if we ignore the boundary, so in the bulk, we have a bunch of tensors. Okay. But now we have several copies of our states. Okay. So for example, on the, we'll have like, say, a site, I'm going to call it 1. We have a tensor T1, and we'll also have a bra. We have a tensor T1 star. But now we'll have different copies. So we'll have a tensor T1 in the other copy, and we'll have yet another copy. So I guess what I'm drawing here is a single site, and I'm drawing 4 replicas. So I'm just saying you take 4 copies of your density matrix. So the tensor T enters 4 times in the kets, and 4 times T1 star is going to appear 4 times in the bra. Yeah. So now I'm going to average. I want to average this, knowing that those tensors are Gaussian. Okay. And so the way we average moments of a Gaussian variable is using Wick's theorem. And so what it means is we need to pair each T on site I with a Ti star, just using that formula, and that will just give me essentially 1 forcing all the indices to be the same. That's what the pairing will mean. Okay. But now I can do this. So for example, I can take my first replica and I can choose to pair T1 with T1 star. But I can also do this across replicas. So for example, I can glue my replica 2 with my replica 3, and so on. So that's the valid pairing, okay, of Wick pairing. Okay. And so that pairing from Wick's theorem, you can label by some permutation of those Q replicas. Okay, so this is some permutation. So this leaves 1 invariant, and here that's swap 2 and 3 and leaves 4 invariant. And you can have all sorts of permutations here. Okay, so this is just basically what you can do at each site. Averaging will give you 0 unless you pair each T with a T star on each site, and you can do this across different replicas. So on each site, you can pick a permutation. That's it. So there's no Weingarten calculus. This is just Wick's theorem. So it's easier in that sense. And so computing, all sorts of traces or whatever, I haven't really specified what I'll do at the boundary, but like doing this average will end up being a sum of permutation, where for a site here will be a tensor. Okay, so for each tensor, I've erased my tensor network by the square lattice I had before. Each tensor I'm replacing by a permutation that tells me how I'm gluing things from the ket and the bra, if you want, across different replicas. And there's going to be some weights. If you want, it will be a Boltzmann weight here that will depend on all those permutations that I had. Okay. Yes, that's correct. So I haven't, like I said, so for me, there will be the boundary, like the top boundary, okay? So I'll have to decide how I glue things. And so there will be a boundary condition. But recall that my tensor network was something like that. Okay. So when I average my, so that's what rho is. So for now, I'm ignoring what happens in the top. But I'm saying you take multiple copies and you average over this tensor. And I'm saying when you do this, you need to pair that particular tensor with a T star that lives in a bra, and you in the different copies that you have. That's still a valid thing, and you can do this on each site. Yeah. 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 So there's also some, very similar physics to the MIPT. There's going to be some transient, and then if you wait long enough, there's going to be a steady state. Okay. That's right. So I'm running it up to some time. And actually, the derivation of the StatMech model will be kind of geometry independent. You can do this for any sort of geometries and so on. Yeah. But yeah, I mean, you can think of it as like in the StatMech language, that's going to correspond to applying like a transfer matrix for a long time, it converging. So that will be like the ground state of the transfer matrix will be describing the steady state.
That cannot be calculated.
Well, I'm going to do this by formulating the StatMech model first, and then we'll have a transfer matrix if you want. Yeah. 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 Well, so Yeah, so this is a non-unitary evolution, so it will tend to just converge to something nice. There's not going to be any oscillations or anything like this here. I mean, the way we're going to see it is like, we're going to see this in the StatMech model. Like for any, I'm just evolving for I don't know how many layers. And for any, this derivation is exact, as Vedika mentioned. Like there's no approximation yet that I'm making. This is 100% rigorous, no problem. I'm just saying I can do those averages for how many layers I have and so on. And I'm just going to map it to a StatMech model. There's no approximation. Yeah. Oh, well, then I will just have those are positive. And so this will just be a nice classical StatMech model. So you'll just have a transfer matrix. If you apply it many times, you're just going to converge to a ground state. There are no phases, nothing here. It's all positive. It's like imaginary time evolution, if you want. Yeah, so that's not going to be the ground state of the quantum system. It's just going to be the steady state, like the ground state of that transfer matrix. Yeah. Yeah, well, I haven't, I didn't get to it. I'm not sure I will. Okay, so I'm gonna leave this mostly as like for you to think about for tomorrow. So then there's a question of actually computing what this Boltzmann weight is. Yeah. So in the unitary case, we'll also have a sum. Like so we'll have a swap thing going on at the top boundary. Okay, so that's maybe since I only have a few minutes. So like for tomorrow, maybe start thinking it is. It's actually not complicated, I swear. So the only thing that happened is now once I have my pairings, I'm forcing indices to be the same. Okay, and so that's all that's left of those tensors. So we just have Kronecker deltas, and doing the contraction is something we'll be able to do. So the picture that we're going to have is we'll have those two partition functions. We'll have a partition function ZA, which will be that StatMech model, okay, defined on a square lattice. And on each side, we'll have now a permutation. Okay, so those will be the spins of the StatMech model. So with Sagar last week, you were doing an Ising model. You had two copies because you were doing purity. And so you had two, if you do permutation of two copies, you only have two elements, the Ising spins. Now the caveat is we have like all those permutations that are kind of weirder to think about. And on top of it, I need to remind you, we need to think of Q goes to 0, which is even weirder to think about, right? But forgetting this replica limit for a moment, we have a well-defined StatMech. We'll write down the Boltzmann weight. And then on top, we'll have different boundary conditions, okay? And that will depend on the entanglement. So if we take a region A here, okay, where we want to compute entanglement, this will have a different boundary condition. And in particular, what we'll show is here we'll have a different permutation fixed at the boundary. So here at the boundary, we'll have some permutation, which is fixed to identity. And here at the top boundary, we'll have a permutation. We'll have that permutation that I talked about earlier. So we'll have a permutation, which is precisely this permutation I started with, which is implementing the Rényi tensor M. So basically doing the Rényi contraction on the M replicates. Okay, so that's what I'll show tomorrow. This thing is in the way. But yeah, so we'll show we have that top. So we'll have to deal with the boundary that to some extent I already did at the beginning, right? So this will do the partial trace and computing. So we'll have that boundary condition doing the wiring, but in the bulk, we have those permutations that just come from Vick's theorem. Okay. Yes. Yeah. Good. So that's actually one like already almost a prediction you can make from here. So all Rényi entropies are defined in terms of kind of the same replica limit of the same StatMech model, but they will correspond to different boundary conditions. Okay, so you see like at the top boundary, this permutation that I wrote here, it will depend like, I'll have n. So like depending on which Rényi you're computing, you're gonna do a different wiring at the top. So the interpretation you should have is you'll have like a, StatMech model. At the critical point, it will be a CFT, but then you're doing different boundary things at the top to compute different Rényis. But in particular, all Rényis will have a transition at the same point in critical bond dimension, or the same PC in the measurement-induced phase transition context. Okay. So tomorrow, what I'll do is I'll finish the derivation of a StatMech model. We'll write down those Boltzmann weights. I'll show how to do like one simple calculation using this, so that it doesn't look too abstract. And I'll discuss how to do the same for like the measurement-induced phase transition problem where you have unitaries. The good news is you'll see that it's very easy with what you did with Sagar last week. It's basically almost the same. So the two problems look very similar. So if you want to just refresh your memory about those Weingarten functions and Schur-Weil duality that Sagar talked about last week, that'll be great, because I'll talk about this tomorrow and I won't go into all the details. But the measurement-induced problem will also have permutations that come from this. You'll just have slightly different Boltzmann weights, but otherwise it's going to be the same. Okay, so that's what we'll do tomorrow. Right, thanks. Questions? Yes.
Boltzmann weights will positive for the measurement phase transition when you have unitaries.
Yeah. So in the measurement-induced phase transition, the Boltzmann weights are not obviously positive because you have those Weingarten functions, and as you know, they tend to be negative sometimes. There are ways of rewriting them as something positive by performing, some partial summations. That's why I think, at least from a purely pedagogical level, the random tensor network problem is a bit easier because things will be positive here, and you don't need all that Weingarten formalism. It just Vic's theorem, which I think is easier. As it's easier for me to see the permutations here. But here, like, things will be, clearly positive. On a more philosophical notes, I don't know if positivity is that important. Of course, if you want to say you have a classical StatMech model, it seems more appealing to say that Boltzmann weight should be positive. But since you're taking a replica limit anyway, that essentially makes things non-unitary. Like the CFT in particular is non-unitary. It will intrinsically have negative weights. So I would argue that even if you have positive weights, it's kind of slightly misleading because I think the actual transition is a non-unitary field theory.
In the measurement-induced phase transition, can you choose a different ensemble of the unitary weights are positive?
Yeah, it's a good question. I don't know because there are not that many cases where we can actually do this. But in principle, yes. So there's in principle, there's kind of a general framework to go from like an ensemble of gates, and you'll have spins which are not permutations, but we can define them formally. And maybe there are cases which are always positive. Or at least the random tensor network is a case where it's going to be nice and positive.
But somehow with the measurement-induced phase transition, you can the ensemble such that it's Gauss.
Right. Yeah. So one nice thing again, the Weingarten formalism that you saw with Sagar is, it's nice, it's rigorous, and so on, but it can be very abstract. Here, like, I don't have this. I'm just applying Vic's theorem, which I hope is okay with everyone, right? I'm just pairing Gaussian variables, and that's all we're doing. Okay. Unitaries are more complicated because of that unitary structure, and that's why you have like those Weingarten weights. Any other question? Yeah.
So if I took your random tensor network and put the whole thing on a torus, so you take the state from there and contract like that, contract that as well, then it's now a StatMech model, but a StatMech model with disorder. And I'd like to see that whole thing as a type of StatMech model.
So why do you say disorder? It will just be periodic boundary.
You have points disorder still on all.
So the StatMech model will be clean.
No, not this one. The original tensor.
Okay. Yeah.
So
So
tensor network itself is each row is an MPO. I
Mhm.
think that as
Yeah.
transfer matrix at some point.
okay. Yeah.
Yeah, so that by itself gives you a partition function. right?
Yeah. Yeah. That's right.
Does that partition function have singularities as you change big G?
So this is okay. So the question is, you can think of like the tensor network itself basically as a StatMech model, is what you're saying, right? You can kind of think of your MPO as a transfer matrix, and like, but of a disordered system. So I'm not exactly sure. So just to be clear, like the StatMech model I'm talking about is very different, right? Because I'm replicating, averaging, and now I don't have randomness anymore. Okay. So can you? So what was the question about like that?
The question was about that partition.
Yeah.
So
And
does
what do
that
I do?
partition have singularities as one?
No, I don't think so, because like it's in the entanglement of that transfer matrix, like of that state as you time evolve, of the ground state of that transfer matrix, that you'll have something. So okay. So now this is a disordered system. If you want, you can think of like the Lyapunov spectrum of that operator, and that will have some properties of the transition. So maybe, I don't know if that fully answers your question. So you can think of that operator, you apply it. It's a random transfer matrix now, right? And yeah, that operator, which is disordered, but you have to think of, you have to define some kind of ensemble properties, right? Because it's disordered. So one thing you can define is like Lyapunov exponents as you apply this many times. This will have some signatures of the transition.
Also, can you talk about the purification properties that you talked about yesterday and also today of that? How do they appear in either either the random tensor network itself or your StatMech network?
Yeah, so okay, I don't know if so one of the problems I gave is about the purification mapping. Hopefully I'll get to the end of the StatMech discussion tomorrow. So the purification problem will basically correspond to like inserting a domain wall that's in time, if you want. So, you can kind of see it in that picture. You can think of like the purification problem as computing entanglement between the top legs and the bottom legs in some way. And so if you want, in that StatMech picture, that will correspond to taking like A here and A bar there. So basically we'll have different boundary conditions. So we'll fix the spins to be like identity here, and we'll fix the spins to be something else at the top. And so we'll have a domain wall, but now like cutting the system in the middle. Okay, so basically in that StatMech picture, you can think of both the purification problem or the entanglement problem by just like different free energies of different domain walls. Yeah.
So I don't have time seeing what the StatMech model is. In the conventional disordered StatMech, you have some random field. Couples to like ideal degrees of freedom.
Yeah.
And to integrate it out, you have some replicated field theory. Degrees of freedom are coupled to each other, different replicated.
Yeah, that's right.
Are the degrees of freedom here only at the boundary where rho is?
No.
Or are they everywhere in the bulk?
They're everywhere in the bulk. So every single tensor. Yeah, so the degrees of freedom are going to be the. No, they're going to be the permutations. They're going to tell you how I'm wiring, like in Vick's theorem, you will have like to contract, each T in one replica with the T star in another replica. The degree of freedom is going to be like that permutation. Okay, so like in Sagar's example last week, again, you had like two copies and you had two spins. One of them was like an identity and the other one was a swap, right? Yeah, so the Boltzmann weights, and I'll show this tomorrow, will factorize over bonds, so it will be local. And it will have a form of, it will have a coupling strength, which if you want will be related to temperature. And there's going to be a weight, which is going to depend on those permutations. Okay. It's not a Weingarten function. I do not have Weingarten function. So this W is just a weight. I haven't specified how much.
Like if you just take two,
Okay.
if I just take Gaussian distributed random rank 4 tensor, then I'll just have to define the delta.
Yeah, that's right. So you'll have the Kronecker deltas, and then you'll have to glue different tensors together.
Well,
Right.
that's the gluing. delta.
Yeah, so you'll have like a tensor on site, and I'll have a permutation that will tell me how like the different T's are glued to different T stars in different replicas. And then so what I have yet to do, and I'll do tomorrow, is I have another tensor on site J with another permutation on, like that tells you how you wire those things on that other site. And you have a physical leg here that like contract them together. That was my tensor, okay?
Sorry, the permutation between the replicas? What's the permutation?
So G is an element of SQ, the permutation group of Q elements. So SQ is, it came from the Vick's theorem, right? So when you do Vick, you have essentially you sum over permutations, right? You glue things, you have to glue a T with a T star. And essentially like the number of terms that will survive Vick averaging our permutation of Q elements, right? On each site.
Average TI, TJ.
Yeah.
You get combinations of, you know, if it's a four-threading tensor, you can have a combination of products of the deltas. That is the case. That is the.
So, okay.
Like the average.
Mm-hmm.
I think it's
Yeah.
TI,
Yeah.
TI, TJ, DAR.
Yeah. Yeah, you'll have those Kronecker deltas, I agree. So I haven't said what the Kronecker deltas are going to do, right? But like, so say I have this permutation. This link that I drew here tells me that I'll have Kronecker deltas forcing all indices of that tensors to be the same as the indices of that tensor. But then I have the same here, right? All indices of this tensor on that replica will be the same with of that tensor. Okay, and then like the Boltzmann weight is going to come when I'll try to actually contract my tensors. So doing that contraction is something we'll be able to do exactly because it's only going to be this. And that's going to give you this weight where like this chi, which will be some Hamiltonian if you want, is called the number of cycles in a permutation. Okay, and I'll define this tomorrow. But
pairs of replicated pairs of T's.
yeah, so here when I drew this, I have 4 replicas, and I'm on a single site. So that's what I'm drawing here. I'm focusing on a single site. I have 4 T's, and I have 4 T stars. And when you do Vick, you can pair them in whichever way you want. Okay. And you'll have 4 factorial permutations, right? And that will indeed, those links will tell you that the indices will have to be the same. Yeah. Okay. Yeah. Yeah. Yes. Yeah, so, okay, so just to repeat, the question is like that calculation, the way I sketched it is, you know, it's crucial that Q is an integer, right? I'm literally doing permutations of Q elements. I'm saying you do Vick's theorem. And the question is, should we worry that at the end of the day, we want Q to 0? And, you know, like I said, yes, you should worry. The replica trick can be tricky. It can even be wrong sometimes. And so what we'll be able to do in an ideal world is only do the calculation where Q is integer. At the end of the day, we need to analytically continue and hope that we can take that limit, Q goes to 0. Okay, but that can be problematic, even like if you want to do like a, you know, dumb example, like we can take a function, I think I have it in the notes. Let's take that function. Yeah, so that function happens to be 0 for all integers. Okay, so if you take n integer larger than 1, this is 0, right? Oh, yeah, so that function is always 0, but of course the limit as n goes to 0 is 1. Yeah, so okay, this is okay, so if we actually want like non-integer, okay, no, there's 1. So okay, this is just a trivial example, right? But just to give you an example of a function which happens to be 0 for all integers, but the limit is 1. If you were maybe too naive, you would say, okay, it's always 0. Maybe if I take n to 0, it's a 0, right? So we're gonna have like that problem, but harder, right? So we'll have to worry in terms of the answer that we get, that we can actually take the replica limit in the end. There's only a solution to that in some limits. So hopefully tomorrow I'll mention that, like, if you take the limits, so here if you take the bond dimension to be large, or in the limit of measurement-induced phase transition, if you take the on-site Hilbert space to be large, then you can kind of really solve the StatMech model and take the replica limit, and you don't have a problem. But in general, it is tricky, and it's also why we don't fully understand the transition yet, right? There are a lot of things we don't understand about that transition. So unfortunately, the transition is not an Ising or something like that. It's a lot more complicated, precisely because of that limit. Right? So if you take 2 replicas, it's going to be an Ising model. If you take more replicas, it's going to be more complicated. But ultimately, what we care about is a limit like this. We'll see tomorrow that for measurement-induced phase transition, it's almost the same, except the replica limit is different. So that will be for MIPT. And this one will come from the bond probability. But in both cases, you have to take a replica limit, and that's going to make things hard. Yeah.
Is there any other way to do it without replica? In some cases, is there a chance for that?
Yeah. So okay. So the question is, can we do anything that doesn't use the replica trick? The answer is, yeah. I wish. We don't have like super great ideas. Like in principle, you know, for disordered systems, there are different approaches. Sometimes people use Keldysh or use supersymmetry for non-interacting systems. So there are like ways around the replica trick. As far as I know, there's no good way around this. Like whatever theory of like MIPTs or random tensor networks, whether it's, you know, there are different formulations of this, but they always replicate the field theories or StatMech models at the end of the day. So at least so far, no one has found, at least that I know of, a very good description of those guys that doesn't use this. Okay. The nice thing is the StatMech model will still give us a lot of intuition in terms of domain walls and, you know, qualitatively what the different phases are doing, how things are scaling. So that's what we're getting from this, right? So we know a lot about how domain walls behave in magnets. So we'll be able to infer some general scaling properties at least from this. Yeah.
I think we better.
Yeah. Okay. Thanks. Yeah. Sure. Yeah.
We look at the boundary and we analyze the bond dimension in the both go to infinity.
Mhm.
So will we have just an easy model, or we will have?
Yeah. So if you do large bond dimension, I think I'll do it tomorrow. But it's going to basically be a 0 temperature StatMech model. You can kind of